So, I would like to tell you something I've been doing recently, and it's almost by chance, I can say. I came across the problem of entanglement non-locality in quantum theory, coming from something that I was doing before, more related with statistical decision theory and quantum theory applying to game theory. And today's talk will be articulated as follows. So I would like to start with a brief reminder of what quantum non-locality is, especially how quantum non-locality is defined, and it happens to be defined in terms of Bell inequalities that can be reformulated actually as some particular form of collaborative game with incomplete information that are usually called in the literature of quantum theory, quantum foundations, as non-local games. And I will explain to you, or I will remind you, what we mean by non-local games. And then, having this operational notion at hand, it will be easy to understand the tension that there exists between two notions that are very peculiar of quantum theory. One is the quantum non-locality and the other one is quantum entanglement. That too often, I would say, are identified, even though they are not equivalent. Or at least, the aim of this talk is to show that the inequivalence between these two notions can be solved by extending the set of games we consider to define quantum non-locality. Anyway, this will be the main result of the talk. Before going there, I will recall you two operational paradigms that are used to describe entanglement and non-locality as resources. These are very useful if you want to quantify entanglement and non-locality, right? And the first paradigm is the so-called paradigm of local operations and classical communication, which is abbreviated into LOCC. And the second paradigm is that of local operation and shared randomness, which is abbreviated in LOSR. And while the first one is particularly natural, or has been deemed to be the natural operational setting to describe quantum entanglement, the second one has been argued by some authors to be the natural operational paradigm to describe quantum non-locality. So we will try, of course there are some alternative proposals, but we will not be dealing with those in this talk. So having these initial notions at hand, I can define later what I mean as non-local utility, which is a function of a given quantum state. So in a sense, it will give you a number that tells you how strong are the correlations that can be extracted from a given multipartite quantum state, and how useful are these correlations to play this distributed game. Okay, I'm sorry. And how useful these correlations are to play in this distributed sort of games we will consider. And then we will actually try now to relate some of these notions coming of a theorem that will give us essentially necessary and sufficient conditions for the existence of a local operation and shared randomness between quantum states in terms of their non-local utility in a set of distributed non-local games. And as a consequence of this general theorem, we will draw a corollary that will tell us very clearly that actually non-locality is there anytime we have quantum entanglement. That was something that was, in a sense, left open as a gap in the theory. And many people didn't like. And today I will show a possible solution to this problem that was the literature. So let me start briefly by recalling you what a Bell inequality is about. So usually Bell inequalities are introduced in a physical setting. So you imagine that you have a common source that is producing bipartite physical systems, in the bipartite case. And one particle goes to Alice, another particle goes to Bob, and we imagine that Alice and Bob live in two separate laboratories, well-separated laboratories. That means that communication is not allowed between the two. Of course, you can imagine that Alice and Bob are honest and they play this game without cheating, so they do not communicate, but there are ways to enforce locality between Alice and Bob, right? For example, usually in the experiments, when you perform this sort of games, you imagine that Alice and Bob are very far apart and that they have to do their actions fast enough so that if they were communicating, this communication would have taken place faster than light. So you can rule out communication by believing or by enforcing special relativity on yourself. Anyway, the setting is that we have two laboratories, Alice and Bob. They both receive particles, and they can choose to measure two different observables. So, for example, you can imagine that these particles are two spin 1/2 particles, and Alice can choose to measure the spin in the direction x, having as outcomes up or down, or choose to measure the spin in another direction, y, for example, and again, the possible outcomes would be up or down, plus or minus 1. And Bob is allowed to do the same, so also Bob can measure his particle along two different directions. And after the day, so after they collected enough statistics, they go back to the same room. They can compute the correlations between their outcomes, depending on the directions they used they chose as measurements, and depending on the outcomes they obtained, and they can compute the correlation function of this form. This isn't actually what was proposed originally by Bell. This inequality is what was proposed in the CHSH paper that appeared a few years after Bell's Flauser, Horn, Shimon proposed inequality. And it is possible to prove that if you think that your pairs of particles can be described by a theory which has some realistic and local hidden variable, then you cannot violate this bound. So the value of this correlation function must be bounded between -2 and +2. Okay, this is essentially the content of Bell's paper, and this is called the Bell inequality, or CHSH inequality. And if you are able to violate this inequality, it means that the theory that describes your particle pair is not of the type like local and real hidden variables. So it is very useful and very instructive to remove all the physics from this, or remove, how can I say, needless physical assumptions, like that of the laboratory, or that of the spin 1/2 particle, or the particular measurement that Alice and Bob performed, and to reformulate this problem as a game, played between two players, Alice and Bob, against the referee. And the kind of game we are going to consider is that which is called a collaborative game of incomplete information, in the sense that Alice and Bob want to collaborate, in the sense that either both they win the game, either both lose. And they play against the referee that will question them. The referee will give Alice and Bob an input, which is separated in this way. So the referee will ask, for example, a one-bit question S to Alice and a one-bit question T to Bob, and will weight them to compute an answer, which is also will be evaluated in 1 bit, either 0 or 1. And then the referee will check in a truth table whether the answers that Alice and Bob computed are winning answers, depending on the question that the referee So for example, this is the truth table describing the CHSH inequality that we gave before in terms of measurements and spin 1/2 particle. So here we have the questions, the set of questions. So the first line corresponds to the referee asking both players the question 0. The second line is the referee asking question 0 to Alice and question 1 to Bob, and so on, until the last line where the referee is asking both the question 1. And these are the winning and losing conditions. So Alice and Bob win if they happen to answer the same bit, either 0 or 1, in the first 3 possibilities, while they win in the last permutation of questions if they answer opposite bits. And this game is called is a game with incomplete information because Alice and Bob cannot communicate the question they've been asking. So it means that their strategy cannot depend on the question asked to the other player. The strategy can only depend on the question. The strategy of Alice, for example, can only depend on the question she's been asked. Okay, this is just to show that this mimics, just to convince you that this is the game theoretical reformulation of the CHSH inequality, because this mimics exactly what we had before. So you can imagine that the two questions are actually corresponds to the directions in which they have to measure. So you want that their outcomes are perfectly correlated in the first 3 instances, while only in the last instance you want the answers to be anti-correlated, as it happened before in the Bell inequality, where if they both were measured in the second direction, then you wanted the spin to be anti-correlated. And with exactly the same techniques you can do, you used to compute the Bell inequality before, you can compute a bound on the average, on the expected payoff Alice and Bob can get out of this game with a classical strategy. And the bound is given now in terms of 1/2. So they cannot win never more than 1/2 yen or pound or whatever for each round of the game. Now usually what you do is to think that actually Alice and Bob can choose a strategy before, and the strategy can contain also the share of classical random variable. For example, Alice and Bob could synchronize their clocks before and choose a strategy to play this game depending on the time that their clocks, which are synchronized, show them. So this amounts to giving Alice and Bob the access to the same classical random variable R. And also in this case, actually, it's very simple to show that they cannot win more than without it.
What is random about synchronized clocks? Say random variable, as example, you say synchronized clocks.
Well, it's just a way to say that their answers can be synchronized. For example, they could say, okay, if we receive the question, from the referee when the second number is an odd number, we adopt strategy 1. If we receive the question when the second is an even number, we adopt strategy 2. Or you would have, it's just the idea that they can access the same, they can synchronize the strategy in a way.
I was just wondering what's random about this, because you said it's shared randomness.
Oh yes, well, randomness would be that you just use this shared reference to choose a randomness, right? Or you could just look, for example, Renato Renner has an interesting paper where he argues that common randomness is very cheap because we are surrounded by background cosmic radiation, and you just have to look at the same. You can just decide, you know, the exact point in the sky where to look, and you can decide that the fluctuation you observe there is your common randomness. Of course, you have to be very careful in finding out where you're watching. But so you start with a synchronization, loosely speaking, and using a synchronization or a shared reference, you can then draw some randomness. But if you think that the world allows you to use quantum theory, then you can imagine that Alice and Bobek's quantum strategy. The quantum strategy always amounts to them preparing a state psi in advance, sharing them, bipartite state in this case, because there are just two players, and sharing this state. And the answers will be computed by performing some operation, local operation, on their shares and performing some measurements with outcome x and y. And in this way, you can show that you can violate that bound. So this is exactly the content of the Bell inequality that tells you that quantum theory cannot be described by a local realistic hidden variable theory because the bound is violated, that you can test it experimentally, modulo all the loopholes that are there in a practical implementation of the experiment, but it is a completely different problem. In principle, you can violate the bound.
So is there some weird bound that you can get somehow with non-stimulating things? So this is so you get between minus half and plus half.
Yes, yes.
Local, like you get between -1/2.
Yes, if you allow, if your only assumption about the word is causality, then you can always win this game. So you can have 1. Expect it to be opposite of 1. You can always win. But here we are dealing with quantum theory. We will always be playing with quantum theory. Okay, so this is just one instance. That was just one instance of a Bell inequality. There is an entire cohort of them. There is a continuum of Bell inequalities. And whenever you violate one of them, you say that your state exhibits some non-locality, in the sense that whenever you violate one Bell inequality, you cannot find a local hidden variable model that is able to describe the outcome of your measurement. So, you can safely assume as a definition that quantum non-locality is that property that quantum states enjoy, for which you can win non-local games more often or more efficiently with respect to what you would be able to do without quantum states. So this is the definition of quantum non-locality, defined in terms of non-local games. I don't want to enter into very intricate philosophical interpretation of non-locality, whether this should be called non-locality or non-Kolmogoroffness or non-contextuality. I'm not interested in these problems in this talk. I will just use the term non-locality as the possibility of violating a Bell inequality. Okay, so now we start instead by introducing entanglement as we introduce non-locality. And the difference between these two notions is that while non-locality is operational, it's defined with respect to game. So there is a very well-defined experimental setup to probe the property of non-locality. It is not so for quantum entanglement, because entanglement is defined as a geometrical algebraic property of a bipartite state that cannot be written as a convex mixture of local states in this form. And somehow, in the literature about quantum non-locality, there's always been a sort of overlap between the two notions. Probably, or arguably, from the Einstein-Podolsky-Rosen paper in 1955, where the three authors are arguing that quantum mechanics is not complete because you cannot essentially know the two non-commuting, the value of two non-commuting observables on the particle, and then they use an entangled state to show a sort of contradiction between their assumption and the prediction of quantum theory. In any case, the first paper where they use quantum entanglement in a non-local sort of way, at least to the best of my knowledge. And from there on, because also Bell wrote his paper as a direct continuation or a direct refutation of the EPR paper. So the notions of entanglement and non-locality has always been interchanged. And this sort of confusion, let's say, lasted until Werner, when in 1989 actually showed explicitly that entanglement and non-locality are inequivalent concepts. In particular, Werner constructed a set of entangled quantum states that are not able to produce non-local correlations. So you can have these entangled quantum states, and whichever measure you perform of them can always, the statistics of this measurement can always be described in terms of a local hidden variable. So Werner was the first really to show that there is a finite gap between the notions of local states and separable states. And from his paper onwards, there's been a lot of research about understanding the relation between the classification of states in terms of separable, entangled, bipartition, versus the classification of states in terms of local and non-local states. So what we are going to do today is to propose a way to solve this gap, to actually prove that an entangled state is so if and only if it is non-local, in terms of non-local games. Okay, before I continue, I need to record you also something about the operational paradigms that are used in the theories of entanglement and non-locality. So the first operational paradigm, it is that of local operations and classical communication. And it works as follows. So we think that Alice can perform some operations in her laboratory, which would be accompanied by the production of some classical outcome, let's say A1. And this classical outcome can be communicated from Alice to Bob along some classical channel. And that Bob, depending on the outcome, will perform some other local operations on her quantum system and produce a second outcome, B1, which in general will depend on A1, and send it back to Alice, which will then do something more, and you can have this operation repeated, right, with the only constraint that the communication happens on a classical channel. This prevents Alice and Bob from communicating quantum systems. So this is, in a sense, the operational framework which is considered natural in entanglement theory, because entanglement cannot be created by exchanging classical information. So entanglement becomes a resource in this operational theory. It becomes something that it can be given, but it cannot be created for free. Well, one could say that this class is particularly ill-defined, because then you have problem of convergence when these rounds of communication tend to infinity. It's not closed. But this is a different problem, and we're not interested in this anyway. But one thing to notice is that however you restrict the communication to be classical, still whatever communication is a non-local resource. It allows you to create non-local correlations, right? You cannot create entanglement, but you can create non-local correlations. Just by, you can create shared randomness for free. And this is not, we can argue that it is not a meaningful assumption when you want to deal instead with non-locality as a resource. So in this case, some authors prefer to consider a restricted class of transformation, which is the class of local operations and shared randomness instead. So you allow Alice and Bob, so first of all, you forbid Alice and Bob any sort of communication. So there is this wall that they cannot bypass. But you allow them to share some classical random variable, as we said before. So today we will be focusing on the framework of local operation and shared randomness. So the main points of this talk will be the following. So first of all, we will construct a necessary and sufficient set of necessary sufficient conditions for the existence of a local operation and shared randomness protocol to transform one quantum state into another. So if I give you two quantum states, two bipartite quantum states, you are able to construct a set of necessary and sufficient conditions to say whether one can be mapped into the other by means of local operation and shared randomness. And this set of conditions will be given in terms of non-local games. Essentially, the content will be if one state is better than the other, if one state gives you a higher expected payoff with respect to the other for a whole set of non-local games, then it is possible to map one to the other, if and only. And as a corollary, I will show you how from this main result it is possible to derive the fact that all entangled states are actually non-local. So closing the gap that was there since Werner's paper. Okay, first of all, we have to make it clear how to extend non-local games in a way to consider more general scenarios. Because before we only considered the very specific non-local games where you have only one input questions, one input answers, and a very particular payoff function or truth table. So from now on, instead, we need to deal with a more general scenario where questions are drawn from two question sets, S and T, which we will take to be finite and discrete. And also answers actually can belong to more general sets, X and Y. And then you have a real valued payoff function, yen of SDXY here. It is real valued for simplicity, but you could take it to be bounded between 0 and 1. So actually, you can imagine that it's a winning probability. But this is not important for what I'm going to say. Okay, and another thing that we will do is to allow Alice and Bob to share a given quantum state Roy. So now we want to describe how good is Roy B to play this sort of games. So you can imagine that Roy B is given to Alice and Bob. It's not part of the strategy. So it's considered as a resource. What Alice and Bob can do is to use that given quantum state rho as a mean to help them compute their answers X and Y when questions S and T are given. So since here we are assuming quantum theory, because everything we want to do is to give a statement which holds in quantum theory, so a theory-dependent result in a sense, there is no harm in imagining that the referee sends the questions through a quantum channel. From the non-locality point of view, there is nothing we lose by this extension, right? Because in any case, a communication channel is a channel that communicates physical systems. So you can always imagine that actually the classical questions are given to Alice and Bob through a quantum channel. And in the case, I mean, you get the usual framework of a non-local game whenever the questions are encoded on orthogonal quantum states. So here you have these two projectors, S and T, that live on these two auxiliary spaces A0 and B0, like ancillas. So what Alice and Bob can do is to decode what is the question. They can do it perfectly because we assume no noise here in this picture. So they can read what is the question that the referee asked them, and then use this as a piece of classical information as before. So there is no problem with this assumption. And you can actually compute now the expected pay off in this way. So here you have a maximum over all possible POVMs on Alice and Bob, and the POVMs are used to compute this joint input-output probability. So you see that the measurement on Alice acts on Alice's share of the bipartite state and on Alice's ancilla that encodes the question S, and this measurement has as outcome the answer X. And analogously for Bob, so Bob has outcome Y, and then here you have this now four-partite state. In the center you have the initial bipartite quantum state rho, and here you have the two ancillas, pi S and pi T. It's a shorthand notation for this projector S, projector T, that encode the questions.
Alice and Bob know the properties of the quantum channels.
What do you mean?
They know its dimensionality.
Oh, they know
how to
everything.
interpret
This is
the-
part of the rule
Yeah.
of the game.
Okay.
So they know exactly how the game will be played. So they know the dimensionality of these ancillas.
They know what that
And they
projector
know-
corresponds to.
exactly. And then here you have the payoff function, which is weighted by this joint input-output probability and average. So this is really an expected payoff. Okay, this is just to say that this is a joint input-output probability. So now this is a function of the game and a function of the bipartite state rho. And we will call these functions the non-local utility of rho with respect to the non-local game G. Now from here we can already derive one set of necessary conditions for the existence of a local operation with shared groundedness transformation. So imagine that Alice and Bob start with a given state rho. And suppose that there is noise acting on their end. So there is noise acting locally on Alice and another noise acting locally on Bob share. And suppose that the action of this noise give rise to another state, sigma, A prime, B prime. Of course, what you have is that the expected payoff that Alice and Bob can hope to extract from sigma is less than the expected payoff they can extract from rho, just because there is extra noise. So it means that they are limited. If they can play the game using sigma, it is as if they were playing the game with rho plus some local noise. So the set of their strategies is limited. So they cannot expect to get the same payoff from sigma as from rho. At least the same, but for sure not more than. And even if the noise is actually correlated through a classical random variable, still the same conclusion holds. Because the classical random variable can be given as an extra resource. So here it just tells you that Alice and Bob are playing, if sigma can be obtained by rho by means of local noise correlated by local hidden variable, it means that the set of strategies that Alice and Bob can employ here is just limited. It's just a subset of all possible strategies that Alice and Bob can play here. So this gives you, okay, so this is the way you write local noise with the classical random variable correlating the two. And now the point is that both these maps for all R are trace preserved. So they happen for probability 1. These are local deterministic noise. And here you already have a set of necessary conditions for the existence of such a transformation. So this is exactly the set of transformation we were considering before. This is the set of local operations with shared randomness. So if sigma can be obtained by rho via this particular set of transformation, then for sure sigma is less useful than rho in playing local games. This is just a set of trivial necessary conditions to obtain. So as a consequence of this trivial statement we said just now, is that all separable states give you the same payoff in all non-local games. So having a shared separable state is equivalent to sharing nothing at all in this scenario. And this works as follows. So separable states are those that can be written in this form, so as a complex combination of local states. And it is clear that every separable state can be created for free by local operation and shared randomness, right? Just with a discard and prepare strategy. And imagine that your local maps create these states locally. And this classical correlation is nothing but a classical variable that was shared in advance. So you can say that for all separable state and for all rho AB, there always exists a local operation with shared randomness that maps rho into, just as I said before, just consider the map that discards rho and prepares sigma A prime B prime. And this implies, as I was anticipating before, that all separable states have the same non-local utility for all possible games. And this is simple because consider two separable states, sigma and rho. It means that sigma can be obtained from rho with local operation and shared randomness. So it means that sigma will perform less well than rho in non-local games. But also the opposite is true. So it means that also rho will perform less well than sigma. So they must perform the same. So it means that for all sigma separable, the non-local utility of sigma with respect to a game is actually a constant that does not depend on the state. It's only function of the game. This is clear because preparing a separable state is part of the allowed set of strategies. And now we are in the quest for sufficient conditions, which are the more interesting ones. So one straight guess would be that actually the sufficient conditions before, the necessary conditions before are also sufficient. So one would guess, for example, that if this condition holds, so if sigma is less useful than rho for all games, then actually there exists a local operation of shared randomness mapping rho into sigma. But this is not true. And the counterexample can be traced back to the paper already mentioned by Werner and generalized by Barrett in 2002, where they construct entangled states that do not allow you to win non-local games any better than you would do with separable states. So it means that you can have here a separable state, and you can have here, for example, one of these Werner-Barrett entangled states, and still this condition would hold, but of course you cannot create entanglement from a separable state by only using local operation and shared randomness. So the set of non-local games as we described them up to now is not enough to give a set of sufficient conditions. We need to consider a larger set of non-local games. And what we do is the following. So this was the setting we had before. So we had the bipartite state here, which was given, and then the game was taking place through a quantum channel, but it was not exploited in full, just we were sending orthogonal states here, and the answer was classical. So what we do is simply the following. We allow the referee to really take advantage of the possibility of sending quantum states through these channels. So now you don't have orthogonal states anymore, but you have states that are labeled by the questions S and T. And the set of states, and you were noticing, is part of the rules of the game. So all these things are given at first, before the game begins, and Alice and Bob can decide their local strategies to win against this sort of games the best they can. So now this set of games, which contains the set of classical, fully classical non-local games, are called semiquantum games because quantum communication only happen in the answer stage, while the questions are still classical. Sorry, the opposite. The questions are quantum, while answers are classical. The rules of a semiquantum game are given as follows. So you have question sets, which are just the labels, and then you have two ensembles of states, tau s and omega t, which are those that the referee uses to encode the questions. And then Alice and Bob will still have to answer with classical answers x and y. And again, there is a real valued payoff function. And again, I stress that this function can be taken to be between 0 and 1 and actually normalized such that the sum is normalized to 1. So you can really imagine this as a winning probability. And you will have now a new set of functions that can be computed from a given bipartite state rho and from a given semi-quantum non-local game G in this way. So you still have a maximum over all possible local measurement P and Q, and here you still have this joint probability distribution, input-output probability distribution, the payoff, and the average. So again, it is possible to prove that if you can obtain sigma out of rho using local operation and shared randomness, implies that sigma is less useful than rho for all semi-quantum non-local games as well, not only for classical non-local games. But now the nice thing is that you can close this implication and prove the equivalence between these two propositions. So this tells you that one quantum state can be transformed into another by local operations and shared randomness if and only if the former is more non-local than the latter. And again, here non-locality is meant as the property of winning non-local games better than with classical shared randomness. Okay, I will skip through the proof, which is in any way quite simple, and it's just essentially a straightforward consequence of the separation theorem between complex sets. If you want, I can give you a brief description of the proof techniques later on after the talk. So let me just skip through this slide, and let me come to the conclusions or consequences, and then I will finish my talk. So the first consequence is the most trivial, and it is something that we noticed already before in the case of classical non-local games, is that all separable states perform the same in all semi-quantum non-local games. So the utility of a separable state is actually not a function of the separable state, it's only a function of the game. The second consequence, which is probably the most interesting one, is that a state now is entangled if and only if there exists at least one semi-quantum non-local game in which the state performs strictly better than any other separable state. So I would say this is an interesting consequence because first of all it gives you an operational definition of entanglement. So now you can define entanglement not just by saying that an entangled state is a state which is not separable, right? Which is sort of just definition, right? And it has nothing operational. It's only geometrical. Here you can actually say that entanglement is that property that allows you to win these games more often than you would do without it. And it is also interesting because now we have at hand a set of games, so a set of experiments that are in principle able to detect entanglement. Even in those states that were entangled, but can detect non-locality, also in those entangled states that were entangled but local, like the set of Werner states. So now you have a set of experiments that can exhibit non-locality in situations where before we were not able to detect it. As simple as that. Okay, this is just a reformulation, so a state is entangled if and only if it is semi-quantum non-local. So in this sense, we can close the gap between, that was left open by Werner. We can close the gap between non-local states and entangled states, just by extending, in my opinion, in a very natural way, the set of non-local games we consider. And the final consequence is also about the reconsideration of the role of local operation and shared randomness. Which now, I mean, after this result is proved, I think that this set of operation becomes the true candidate for a resource theory of non-locality, because it seemed to be able to capture very well the distinction between local and non-local states. But also, this result gives you the possibility of constructing device-independent entanglement weakness. So, a way to test entanglement even if you don't trust your measuring apparatus, which is analogous to the detection of non-locality in a device-independent way in this sense. So, it might have some consequence in quantum cryptography, for example. And again, as I was mentioning before, it gives you an experimental signature of quantum non-locality also in situations where non-locality was undetectable. So this is just the first step toward understanding this relation between quantum non-local games and locality in quantum theory and separability in quantum theory. And yeah, that's all. And if you have any questions, please. Thank you for your attention.
Questions? I have one actually. Since it didn't show the proof, I'm not sure. But the second consequence, so if I give you an entangled state,
Yes.
and you construct a semi-quantum game, which
Yes.
can be...
Fortunately, the proof is constructive enough
Okay.
to allow you to do that. So essentially, so this is a good question, and this is where Gisin's group is working. So actually, because they want an inequality exactly, so you have to find this hyperplane. But the idea is that you take this family of states to be informationally complete. So essentially, you can take this. Suppose you have 2 qubits. So one way you can choose the states are the 6 states pointing in the 3 direction of the spins, x, y, and z. Or you can take these states to be the 4 tetrahedron state on the block sphere. So the point is that you want this state to span the local state space, or a set of density matrices. And then you can take these two measurements to be the Bell measurements. So essentially you have the given state, you have these 2 ancillas that are sent to Alice and Bob, and then Alice and Bob just measure the Bell measurements on these 2 particles that now they share, and you can prove that the joint input-output probability distribution you obtain if your state is entangled cannot be obtained by local hidden variable theory. So then you have the convex set of input-output probability distributions that allow a local hidden variable model, and you have one point outside it. So now what you're left to do is just to find a hyperplane dividing the 2. The hyperplane will be the definition of the payoff. But this can be done very efficiently. It's a linear program. So if I give you one state, so you get one probability distribution, actually, the nice thing is that this is what the student Denis was doing. Is that actually you can see that you're lucky enough that for the whole family of Werner states, intuitively enough, because it's a one-parameter family, there exists one fixed semiquantum non-local game that reaches the separability threshold. So you can really test the non-locality of Werner states. Modulo the preparation of these things, which is probably, and then Bell measurement, which is always complicated to be done in the laboratory. I don't care how the orientation is taken.
So I did a question related to the Barrett 2002 paper. So in that he shows that if you have non-sequential POVMs on Werner states, then you find a local variable. So as far as I know, the sequential POVMs was still an open question, right? Whether you could increase the entangled Werner states that do not have. Can you actually use this method to?
Well, these two methods are inequivalent.
Yeah.
And what I know is that also with sequential measurements, the gap is still there. It's a bit shrink, but the gap is still there. And there is nothing very much done after Popescu proposal of this, I think, to the best of my knowledge. And a problem could be that you have that the set of LOCC, because then you allow post-selection, so you allow a round of classical communication. It's not closed.
Yeah.
So you cannot really take a limit. You can say, okay, let's do one round of communication. Okay, you shrink the gap up to this point. Let's do 2 rounds of communication, and supposedly, I think that you will shrink this gap a little bit more. Probably you can close the gap with an infinite round of communication, but the problem is that your transformation is no more LOCC. It becomes a monster. So I'm not. I don't think that is a viable way. I mean, this gives you a way to solve the problem in a. Probably is the cheapest way you have to close the gap. Also, there is another proposal by Luis Masanes, Doherty, and Yang, where they play only one game, the CHSH game, and they give Edison Bob the possibility of sharing an extra entangled state. An entangled state,
This is the activation.
an entangled state which does not violate CHSH, but notice that might well violate other than inequalities. So it's not clear what is the role there of activation. You're really giving a non-local resource to Edison Bob, so it's a bit more difficult to argue that. In this way, there is no way that Edison Bob can cheat because they're just receiving local ancillaries who do not carry any correlation. There is one criticism against this approach is that now you have a notion of non-locality which is theory dependent. Because if you only have boxes, right, with 2 inputs, 2 outputs, you have a description of non-locality, a definition of non-locality which is theory independent. You don't know what's inside the box, it could be whatever, right? You would have squeeze, and then you would be able to always with CHSH to have a PR box. While here, I'm assuming that you're playing the game within quantum theory. But I think it's fair enough because the problem was there in quantum theory, so there was a gap between separable quantum states and local quantum states, and the gap is closed within quantum theory. I think that you can extend this sort of approach also to generalized probabilistic theories. I don't see so many problems, but I don't know if that is.
It's the entangled effects combination.
Yeah, I mean you can define separable states, just a convex combination of local states. Then maybe you don't have pure entangled states, but that wouldn't be it.
More of a remark. I find it very interesting that LOSR turns out to be a good paradigm that gives you this congruence between non-locality and entanglement. It reminds me actually when you go to the EPR paper and you read the 1935 EPR paper, they do not speak about non-locality.
Yes, they do
What
not.
they say is you have two systems that interacted in the past
Yes.
and do not interact anymore.
Yes.
This is very much like a barrier coming
Yeah.
down. There is this resource they share,
Mhm.
which may come from the interaction in the past, but now they don't interact anymore. So in spirit, LOSR is actually quite close to violate in the original.
Yes, in the sense, if you allow Alice and Bob to play LOSR transformations, it means that you are giving them the possibility of exploiting any other local hidden variable theory of their choice. So they can have any other no-signaling local hidden variable theory and use it to transform their state.
Yes.
Somehow you can interpret it in this way.
Yeah.
But in a sense, EPR were playing a non-local game somehow. It was like guessing. You measure, the spin here on the right branch of the experiment, and you guess. You can always win and guess the outcome of a hypothetical measurement along the same direction.
Yes.
So non-locality somehow was.
So you phrase this stuff in terms of non-local games. You thought about how else it might be presented. So for instance, when you talked about the non-local games originally, not these quantum games, I can look at this and I can see, okay, if you just give me a setting for Alice and a setting for Bob, you have notice that you have this table, and if you choose the ones that you highlight in green or whatever, the probabilities of these things highlighted are inequalities. You can see how this comes about. I don't see it as clearly trying to come up with some other way of thinking of your semiquantum games. So is it something like you choose a probability distribution over settings, or is it something more
Yes.
that you, I mean, is it really just that, or is there something more quantum?
So let me go to the slide where I have.
There's your answer.
So no, there is nothing more than that. So the only difference is that here, so before the referee actually draws the questions from these two sets with a priori probability distribution, but that doesn't matter. And then encodes this question and sends it to X probabilities.
Maybe it's so I'm not sure I'm totally understood. I mean, you come up with some. Does this mean you have to come up with some modified form of Bell inequalities?
Yeah, if you want to imagine in this way, yes. So Bell inequalities. So there is also a historical reason probably why classical non-local games are the usual ones considered, because in Bell inequalities you have that the measurement are conditioned, the measurement that Edison Bob performs are conditioned on this classical label. Right? So you have a classical label condition. In this situation you have a quantum state that conditions Edison Bob measurements. In a way, you can state that semi-quantum non-local games are non-local games with quantum side information, if you are familiar with this nomenclature from quantum shannon. So there is no more a random classical variable that conditions the measurement, but you have a quantum state that conditions the measurement. So it's like playing a non-local game with quantum side information.
I suppose geometrically it's more in spirit to an entangled witness.
It is, of course.
Yeah.
This is an entanglement
Because
witness.
I think,
Also, Bell inequalities are
but
inefficient.
they're in like
entanglement
space of probabilities as opposed to this the space of states. Right?
Yes, exactly. A nice point is that these are device-independent entanglement witnesses, because entanglement witness is just an operator, right? It can be measured locally, and then you have a bound. But suppose that Alice and Bob have like bit faulty detectors, and they might well deem one separable state to be entangled just because they have faulty detectors, right? While here, Alice and Bob have to do their best, right? There is that maximization. So if they have faulty detectors, they might say that an entangled state is entangled, but of course they will never say that a separable state is entangled. interpreted as a way to write